Good morning, everybody. Welcome to class. Happy Friday. We are going to finish our discussion on linear regression today. And as I told you last time, today's session will be a lab session, by which I mean we are going to walk through code and kind of relate back to the things that we have covered and see how they are done in R. I have told you there are some of you who would prefer to work in Python, and I would probably make some side remarks in terms of how Python could be used, but this will be dedicated for R. But I also want to encourage you, Python speakers, to use, to know how things are done in R, just for that reason alone. So it will be focused on R. And we will have a lab session of this kind for other discussions that will come next down the road. And so today is the true conclusion for the 3 lectures we have had on linear regression. Before I get started, let me see where we are now. Helen has done a very good job grading assignment 4 fairly quickly. And so the first batch was the 475 students. She completed that, and I reported midterm grades. And then she completed the 575 students also, which means now we were able to post everything on Blackboard. So if you haven't seen, it's time to go check. But I know you have seen your grades. I am very happy. I'm very happy on how things work. I did not grade it, Helen did, so the credit is due to her. But I was happy to hear that you did a very good job on the map question. I think it was fun where you grew up, and I think you proved to yourself and to me, and you could do these things on a visualization that is a non-trivial thing. And so you should be proud. I'm going to go ask Helen if she had a favorite, so that there will be one that we can share. Here is one solution, because I think most of you have done them correctly, but there may be some that are nice looking than others. And so I would probably find out what they are and tell you. Let me stop sharing this while I talk. We will do that. And the other thing we will do is the word cloud was also a fun exercise. And some of you have done something around things that you would have some relationship with what you wrote. And if there is a favorite that Helen has, that will be posted also. Other than that, and so this was the first 4 assignments, we are going to have a new assignment today. And I'm going to talk about that in a second. But the lab session will start soon. The reason I had those pictures that you saw on the slide, it was about walking. And so today's warm-up question has to do a little bit with walking. It's halfway through the semester, many things are happening. So I want to understand that there will be some level of stress, but make sure that you do walk, right? When you get a chance. And because now the weekend is coming, I hope you'll get a chance to walk for, 15 minutes, 20 minutes, or half an hour. And so the warm-up question for today, by the way, will be written by, I'll start with a fun fact. There are 2 Chris's in this class. And you probably know one Chris because I always use him to go to Blackboard. So Chris, the other Chris, be ready to do that in a second. But we've got another Chris, Chris Roberts. He will be the one to have the honor for writing today's warm-up question. And so Chris, this is what you will type. I know many of you are in Pullman, but some of you are in Tri-Cities, some of you are even some other places. So go to the place where you are, start with the city, tell us what it is, and then tell us what your favorite walking trail or hiking trail is, the name of it. So what is your favorite hiking or walking trail? For those of us who are not in Pullman, please tell us where you are so we know. And the next time we come to that place, we make sure to check that out. Chris is going to type the warm-up question. The question is, what is your favorite walking trail? I'm not seeing Chris typing. Oh, yes, he's typing it. Perfect. That's the question. You go ahead and participate, and I will let you know what we have for that one. This other Chris Cree, will take over the screen now. I hope you are there, Chris. And I want to point to Blackboard because assignment 5 out. Yay, Chris is there. So go to content. And we'll see assignments right there. And so there is a new one, assignment 5, if you could open that. And it's a PDF. Perfect. So I'm going to use a minute to tell you. So we first of all, the syllabus says we will have 5 assignments. So this will make it the last one for the semester. The first 4 assignments are completed, graded, and you did well. This will complete the set of assignments we have. It is different from the assignments we have had so far in one way. And that way is it's bigger. One way to do this would have been to split it into 2, and you will have 6 assignments. I didn't think that was a good idea. So it's called assignment 5, but it really has got 2 pieces to it. The 2 pieces are regression, which is what we have finished, and classification, which is what's going to come next week. Because it has got these 2 pieces, it looks back on what we have done, and it looks forward on what we will do. 1 week, like we have been doing for these other assignments, will not be fair. You will not be able to do it. And I don't want you to be extremely stressed either. And therefore, it's going to be due 2 weeks from today. It's being released today. It just released 9 a.m. today. It will be due exactly 2 weeks from today on a Friday midnight. For the first half of it, that is about regression, you have everything that you need to have covered, including the one that we will discuss today in terms of a lab session, walking through our code. For the classification part, you don't know because you haven't learned, but it is a good thing to know what the problems are. I'll ask you to scroll down, stay in the first page. Yeah. For the classification part, you will know what the problems are, so you anticipate them. So actually having them ahead of time is a good idea. So let me tell you the regression problems. Now you can scroll just a little bit so I can start looking at problem 1 and 2. Problem 1 so both of them are regression. Problem 1 is shorter, problem 2 is longer. Problem 1 would talk about a data set that you have seen in one occasion, I think in one of the assignments. It was about auto data set, and this data set is available on the course's website. You will get it. And so there are certain things that we just covered, in fact, in the very last lecture about how to see residuals, whether you have a diagnostic plot and you try to see whether something is linear or nonlinear. That type of question would come, and that's what it would ask you. So there are 3 pieces to it, and it would carry 15%. Question number 2, now scroll up a little bit higher, is going to be on a data set that we will visit today. And that's why it says we saw in class. You haven't seen it, you will see now. And this data set has got something interesting, and this will take us through simple linear regression, multiple linear regression, interactions, polynomial or higher order, that type of things that we have all covered. One at a time will come. And so this has got a larger portion. All of it has got A to E, and if you add them up, it will take for 50%. Now you scroll up even more. Okay, so that is regression. The next 2 problems are on classification. The first one is on logistic regression, and there is no data set, nothing, but you will learn logistic regression first thing next week. And so I want you to know the theory behind it and be able to manipulate things and so on. And it's got a 15% weight to it, and that's all there is. Problem 4 is significant. This is going to be a mini project in some ways. So in fact, if you think about how this assignment is designed, it will set you up in a good way for the project that you will be doing. And I am going through your project proposals. I didn't forget that. You will hear back from me. Everything that I am seeing so far is great, your team makeup and things like that. But you will formally hear from me whether you are approved or not, or feedback I have on them as soon as I'm done. And so you may expect this one early next week, Monday, for example. But this will set you up, and you will get to do something that actually is a mini project in some ways. And this is a classification problem where you are given a data set about articles that are drawn from Guardian, a newspaper, and you are going to place it in one of the several categories that this columns would come from. And you will use an algorithm called naive Bayes, which you will learn. And so there's a good portion of, getting your hands dirty, doing with tokenization, working with text data, and trying to classify with an algorithm that you would learn. So it's got 2 parts. Part A is tokenization. It takes 20%. And if you scroll even more, Chris, the second part is the actual classification where the algorithm is used, and you will have to work with, you can get better at it by having to be careful in what features you select and so on. That will take account 20%. So the classification problem, this problem 4, has got 40%. The regression problems have had slightly less weight, 15, 20, 15, 30, and 15 points, and all of them will add up to 100. This is due 2 weeks from now, and I wanted to introduce it to you today. And plan your time, especially for the thing that you have already covered. Give it a priority. And for the thing that's coming, make sure that you attend the lectures in a good way so you know how to solve this. That was my introduction. So thanks, Chris. You can give me back screen share now. That was what I wanted to tell you about assignment 5. I am reading through your project proposals, and you will hear from me when I am ready. And I'm going to start walking through our code today and to see a lab session. So let me close this one. I don't need it anymore. And start sharing. If you have any questions, you may ask now. Okay, by now I hope you have all participated in telling me your favorite walking place. If not, go ahead and do that. Okay. Do you all see my screen now? I should see, okay. I have got multiple screens, and now the faces that I was seeing before have turned it into a different screen on this way. So let me see if there is somebody who could give me a thumbs up if you see the Art Studio session. Yes, I got 2. And I'm going to also go here and check this chat session and bring it up here so I can watch out if there comes questions. And this one also up here. Perfect. Okay, so I'm going to go up all the way to the beginning. For those of you who would follow along by opening your RStudio, that's perfect. I will run the code and we'll see how things would be. And so I have an RStudio session opened here. And if you really wanted to, I don't comment on the codes, and so I'll explain them as we go through. But if you wanted to read something along these lines, there is a section in the book, section 3.6, that kind of has got a similar purpose. It probably has got the same example, but it may have more things to it. That would be a good place to read. So section 3.6, just note it down. You may want to know. So I'm going to start by telling you the data set that we will work with. And probably we haven't had a chance to see an R code in a while now, but we begin by installing a library and things like that. And there is a command called library that would do that for us. And this is a good example to see it. And so what I am done in the first 2 lines here is install 2 libraries. They will be accessible for us now in this session that we would work with. So the first one is called Mass, and that's the short for Massachusetts. And this is a data set that is available in standard R. And so we don't need to do much other than to get access to it. And that's what we're doing here. Okay, so we are installing that, means that library come and it's available. The other data set is called ISLR. This is the same book that we have been referring to when I was discussing the introduction to statistical learning in R, and you know it. And they also have an accompanying set of data sets that they have their own, that they made it available. And so this is one thing I also want you to know. Some of you are doing research, and so you may have something that you would think people would benefit from. So R has got this community-based stuff, both in code but also in data sets. So you could actually have your own library data set added, and you could give a name and people could include it. And so anybody then would have, they have some strict requirements on how you document stuff and how you talk about them. But these people have done that. And so that's why we are doing this library ISLR that will give us access to the data set that we will work with. So we'll start with simple linear regression, okay? And I'm running through the code. As you see now, it gets displayed. I'm sending it to the console every time I run a line. And that's why I said it will be okay if you just follow me along. But if you have your own, it will be also fine. So Boston is now the data that we will be. Massachusetts with the library. And so there is a data set called Boston. And so we wanted to find out what it is. And so we wrote names. That's a keyword in R. And you give it the name of the data frame that you're working with, in this case, Boston. And so you get some quick summary. So here are variables or features that are there, and they don't tell us very much, but we get a bunch of them. So here they are. If I wanted to know more, because this is a data frame that is available as a library, I could query just like I would query a function, and that querying is done in R by having a question mark you followed by the name. And so in this case, question mark Boston. And if I do that, then I get a nice display of this documentation. This is what I meant. If you were to contribute your own, you will have to be able to supply so that something like this would come out. And now you can see what this one is. It's a housing value in suburbs of Boston, and it's got 506 rows. These are the cases, and 41 columns. These are the features. And so the format is you've got this variable names. Cream is the per capita crime rate by town. These are different towns, zone, some business, proportion, and so on. And so there are a number of variables like this. And in fact, if you scroll all the way down, you could also see which one, when this data set was collected, and there's an associated publication. So it's a bit old, the 1978 and 1980. So whatever it is that we'll see now, we should take it with a grain of salt. It may not reflect through Boston nature today, but that's not our purpose. We are just going to explore this data set and see what it would tell us. Okay, so now we know how to query. I'm going to go back to where I was here. And the first thing I want to do is plot. And what we would plot is, plot, you remember, is an R function. It will take something versus something. And so in this case, it will be the median value of a house. That's what the MEDV is, the median value of a house. This is about real estate. And L stat is the one that has got with low income. The L is for low income. These variable names are people's choice, right? So they could have called them whatever they want. And so the median value of a house versus the low income status. So there would be some neighborhoods where people have high income, and there would be some neighborhoods where they are low. And so the L stat is an indication for that. So that's what the plot is doing. And we are giving it what to plot against what, and what data to use, what data frame to use. And the data frame to use in this case is Boston. So let's go ahead, plot. There we go. So now we have a plot that's not so very nice. It's kind of tiny, but you get the idea. I hope you are seeing my screen. So we got a plot, median value of a house versus low income state. And it looks like, the higher the lower income status is, the lower the value of the house is basically what the story is. And that makes sense, even though we don't know all of the details there. So we now plotted. And it looks like there is a relationship, there is correlation, and it looks like it is a negative one. So the first thing I want us to do is to do a simple linear regression model on it, on a simple. By simple, I mean there's only one predictor. So we wanted to, LM is the linear model. This is a call for a function in R. This is how you get a linear model. So what do? You get the response, you write it on the left, and you do a tiddler, that symbol, and then you use the response variable, the predictor, and in this case, L state is what we want to see. So just right there in line 8, I have now created a model that's a linear fit. It's a simple model where there is only one predictor, and so there we have it. So we've stored this in a variable called lm.fit. This is a variable name, so we just have captured it. And so it's a fit is what we're trying to say, and it is a linear model, and so that it has got that name. You could also have done what I have written in line 9 to, what do I do in line 8? Oh, this is because the Boston was available as a library. I have run this one before, and therefore this line 8 didn't have any problem. For those of you who are following me with an R studio open on your own, it might have complained MEDV is not known or something like that. When that happens, you have to specify for your session to know what data you're working with, and that's what my line 9 is doing. So in my case, it's going to be a redundant line. It will not produce anything new. Line 8 and line 9 are the same for me. For some of you, if you were to run this, line 8 may give you an error message because it would say MEDV is not something that I know. And so you could do that by having to bring it. Another way to do this, that's why I wrote line 10, is to attach, and we'll see an example of this later on. So you make that library and have the variable associated with it in this way. If it is not accessible, then, and if the workspace that you have has got variable names that are in use, then by explicitly attaching it, you get access to that. Okay, so in my case now, I get a little bit of more information about LStat. Okay, what I have done so far is introduce the data set. I have told you there is a plot we have done, and we now know that there is a relationship between the median value of house and low income status. And so I'm going to start exploring this model, just the one that we created called LMFit, and see what it does. Line 12 now is going to give me information about this. This is a model. Let's see what happens when I try to print it. In R, when you write a variable or data frame or something like that by its own, then you get some information that's a very high level description or something that will tell you a little bit about what it is. And so when I write line 12 now, I get this. LMFit, it will tell me what it is. First, it will tell me that this is a linear model. That's what the call means. And so the formula for it is median value is TIDLA, LStat. Here is the response, here is the predictor, is what it is telling me. And then it tells me this very basic information about it. The intercept, that's our beta 0, and the coefficient, the relationship between LStat and MEDV. And as you have probably guessed by looking at the plot we have had, the relationship is actually a negative slope, and that's what this is telling me. That's all I would get if I just write this line, the name of the function, the variable that I created by fitting a model. If I wanted to know more, I can write summary, which is what I'm doing in line 13. And if I write summary, then I get some more. This some more is quite substantial information. And here is where it begins. So you have noticed I was having, whenever we discussed different things in the lectures we have had so far, I was bringing a table and I would show you t-value, r-value, p-value, and some of the slopes, the intercepts. This is information you would get, just that summary would give you. So the function, the call, the formula first given, and then you've got residuals in different ranges, median, the third quarter, the first quarter, and the max. And then you've got the coefficients, which is what the tables I was telling you were. In this case, there is only one predictor, and so there is only one slope I have. Otherwise, I have an intercept. And then I have the estimate, the standard deviation, the t-value, and the p-value. And as you can see, the p-value for the intercept is very strongly significant. There is a relationship between them. And so you get information like that, and then you also get information about the R-squared value, adjusted R-squared value, more than you probably care. So you've got a more or less complete information. That is what line 13 has told us. Great. We could also get some of the internal workings of this fit by having to use names, just like what we used names for the Boston data set, and we got the description. We could also get the description on this model. And so here we go. If I write names and I've got the fit I have just created, I get the coefficients, the residuals, the effects, and so on. Very many of these are used internally in R, but if you were to work with them and you've got a little bit more sophisticated things you want to do, you have access to them. And now you just know the name, but you could query them. You can get one at a time, depending on what your need is. So one of the things that you could, for example, do is to look at the coefficients. And you could call, there is something called coefficients. And the shorthand for the function called for it in line 15, as you can see, is coef. And if I do that, then I get just the coefficients. And so now you see the intercept and the LStat. So all of these things that are associated with the model that you have values for internally in R, you can call them by appropriately calling the function that belongs to it. So coefficient was one. Another thing you would probably want to do is look at the confidence interval, and that's what line 16 is doing here. So if I write conf int, then I get the confidence interval, and the standard thing that R does for you is give you the 97.5% confidence interval and the lower 2.5 confidence interval for the coefficients that you have, and that's what you get when you write conf int, as I did in line 16. Okay, now we fitted a model. Oh, great. A simple one. Simple linear regression is what we saw, and we explored it, and there are some informations that are inside that model that we can query and get. But we would want to do this to predict. And so once you have a model, then you can predict on a value that you haven't seen before. So now if there is some other place we want to find out in the Boston data set, for example, now, and we wanted to predict, we call this function called predict. That's a call for a name, a function call. And then we tell it which model we are going to, the fit that we have created. So LMFit is what we are working with. And then we are going to tell it which, the point on which we want to to get predictions on. And so we have to explicitly frame this as a data frame. That's what the parameter choice shows you there. But we have created a value where there is 5, 10, and 15. These are the places where we want predictions on. And so we created that. And we wanted to specify what confidence interval we would like to have. And we can also specify what predictions we want to have on it. This is a call for now for getting a prediction based on the model we just have created. And so there we go. So when we wrote the confidence, when we asked for the confidence interval that we will get with this, for these predictions, we get a lower and an upper bound, and here we have the values. For 5, the prediction is 29 point something. For 10, it's 25 point something else, and for 15, it is 20.30. And you can see this thing is decreasing because that's what we would expect. The relationship between the two variables, the median value of a house and the low income status, was inverse. The slope was negative, and so the higher the value we give, the higher, I mean, okay, this is very confusing. That's what they chose. The higher a place is of low status, okay, which means the status is really lower, and then the median value would come down. It's what the prediction said, which would agree with what we would expect. Okay, that was values we queried about confidence. We could also query about the prediction, and we get something similar, and we're done. I want to show you now how to plot what we just did. The plot we are going to do now is going to do a plot of LStat and MED-V. And so let me do that. When I do that, I get this MED-V plot, exactly the same thing that I did before. This is because this has become smaller because I was playing around with this, and so I had a pane that was made for 4. That's why you see these things one at a time. I should have turned it into a 1, but that shouldn't bother you too much. So what you see on the left and what you see on the right are exactly the same thing. So I plotted MED-V versus LStat. This is what my plot says. And I want to put a line on this. You've done this when you were doing one of your graphics, graphics exercises. And the way you do that is by calling this function called AB line. And you will tell it what line there is to put on. And in our case, we want to put the fit onto this data set, and that's what our AB line will do for us. But we wanted to, I'm not sure if you see it. Oh, it's not easy to see. So I'm not sure why it's, I think it's got too small for it to be visible. So I'm going to proceed, and I'm going to make it the color red so that it will be visible. My next line will probably save me. Let me see. Yes, so the reason you didn't see it before was because the line was black. Okay, now you see it. So the fit is the red line that you see, and I did that by having to plot. I used the AB line when I switched the color to red. Now you can see it. The other things, the next few lines that you would see has to do with plotting. It has nothing to do, or not so much to do, with the linear fit model we're discussing now. So we changed the color. We could also change the size of the plotting points that we would use here. In this case, they're just simple circles, but we have other choices also, and we can change their sizes if we need. And so here we come, but when we change the, not just the plotting points, the scatter plot itself could also be changed, which is what line 23 has done for us. And I'm going to change now the plotting characters from being what they were into being a plus. Okay, and that's what I would get when I get the plotting pointers to be a plus. R has got very many. So the usual thing when you don't do anything in the scatter plots will be to have dots, but you can make them circles, you can make them triangles, you can make them other shapes and so on. And there are very many of them. So I'm going to show you 20 of them. And this will be fun to just see what they look like. And here they are. And so the plot now is taking, 20 by 20, and all you have done is the plotting characters are plotted. And so you can see all of their shapes as the picture on the right shows you. And this is what I have done. This is why you are suffering from having to see multiple panels, because I did this par where I have a 2x2 panel. That's a code I had run before. That's why my display was still 2x2. So it's not going to change anything for you now, because it had been that way I didn't set it. And so I'm going to plot now the diagnostic things that I discussed last time. This is what your assignment 5, problem 1, asks you to do. And we looked at this one in the last lecture where I said some relationships, and we kind of saw this medium value of a house and the low income status. There was something that it kind of decreases, but it was not really quite linear. You've seen it. And when we fitted the AB line and drew on it, we saw that the points were, the spirit of it was captured, but there were many points that were kind of not really captured. And so there was some non-linearity that we saw. And this becomes very clear now when you do these diagnostic plots. And this is what you see now in these 4 plots. And so the plot I just did in line 28, which is what you see displayed here, has got 4 pieces to it. I don't want to spend too much time telling you all of them. You can, query on R and get help and try to understand them. But the first one is enough for what I wanted to show you. I showed you last time this trend is when you have a residual versus fitted value plotted, you will see that trend curved upwards when there isn't anything about non-linearity that would stay flat. And so this one suggests, and we see it. And so now you know how to do it. I told you last time you plot something like this, but this is automatically done by R for you, is what I wanted to show here. Okay. So I can continue now and show you the different plots. So one of them was enough to show us the nonlinearity of it. But if you do an R student version, then you would also get some of this outlier, some of these things around leverage points. So the outlier detection, which values you should probably ignore from your model, would be obtained when you look at the standardized or whatever R student version of the residual plot. For finding out the leverage, these are the places where your predictor have got a whole lot to say about your model. Those are what the leverage points were. There is a function called hat values, and these people have some sense of humor sometimes. So this hat values is the name of a function, and it was called like this because the function has a hat on it. If you go back and try to remember what I showed you on the slide, when we discussed this, the formula for it involves a hat, and therefore the function is called hat values. I have also maybe incidentally told you about R functions in other occasions, like the C you saw before. When we were predicting new values, it's a function called C you're creating. And for those of us who are in computer science, those will not be a function name. You will not call something just a C. I mean, you'll give it a descriptive name. So there is a difference in culture. Some of these function names have funny names. Some of them have just one letter, and it could be confusing. So I just want to maybe say it, but I want to say it politely. So this is what the hat values would tell you, the leverage points. And so you can find out which ones has got the highest hat value by using this query function called which, and you can find out which one has got the maximum value out of this one. All right, that is enough for me to, with regards to simple linear regression, and I'm going to go to multiple linear regression, and you can sip your coffee right now. If you are following along. How are things going? Can I see in the chat? Or? Okay. All right, thank you. Okay, so we are going to do multiple. What happens when multiple? You've got more predictors to use. We did have this Boston houses, and the median and median value and low status was what we saw. Now we're going to add age, and this is not the age of the owner of the house. So the person who lives there, it's a house, the house itself, how old it is. And so when you add it, if you want to add it, if you just wanted to add one variable to whatever existing before, you use a class like this, and you could keep on adding. So whatever it is that you want to include in your model, in your multiple linear regression model, you can use the symbol plus to show that. And so line 36 now has created a model that is going to have the median value predicted when LSTAT and age are the two, mid value is the response, and LSTAT and age are the predictors. We're still working with the data Boston. Okay, so when we do now a summary on this new fit, where you're reusing the variable, computer science students do not have any problem with this. Some of you may probably need to be reminded if I have a variable and I had associated some value with it, I could use that same variable and give it some new thing. I will forget the previous one, and what I will have now is the newest, right? And so now lm_fit is not the one that we had before. Now it is a multiple one. And so the summary now will give me whatever new thing that is. So lstat and age now showed up. Before they were only one thing. You had only lstat. Now age is coming. But one thing you can see, this age is, it's not as significant, the p-value, as lstat was, but it is still significant because the p-value is less than 0.05, as you can see. So that's what my summary told me. But I could also have more. I could have everything. And what line 28 or 38 is showing, this new model that I just did, is medv, tidla, and now I use dot. Dot means take everything. And we remember this has got 14 or so predictors. And so that model now has all of the predictors included. And so if I do a summary now, I get a whole bunch of them. All of these things that are there now are there. And you can see R would also tell you when the p-value is significant or very highly significant by having these stars associated with it. And so very many of them have got at least 2, but some of them have got 3, but there are some like Indus or age that doesn't have stars. So the p-value now is all of a sudden high. Why? Well, this got this 14, 15 variables to predict. Age, when it was just added to the lstat variable, it was kind of significant. Now all of a sudden it is not, because in the presence of others, then it's no longer going to be significant, which means it is correlated. And so something we discovered now by looking at this data set is a variable could be contribute something when it is just the only one to be selected, but in the presence of others, it could be not significant because of collinearity, something that it is related with, and therefore is not helpful anymore. And so some of the methods we talked about last time to find out which ones are the best, but this itself will tell you. So you may probably be just better off leaving out the ones that are not contributing here. But you will not be able to do this if the number of predictors is very large and you cannot just eyeball them. And so you would use some of the methods I told you last time to find out which ones to use. Okay, you could then say, okay, age is not helping, so I'll kick it off. And so the way you do subtract, you remove, is by having the model before. I'm going to call the new one now where age is removed lm_fit1, a new variable name. Whatever I had before, minus the symbol minus now in line 40 would do that. And so if I do a new summary on lm_fit1 now, you would see that age is removed. Did I do that? Yes, age is removed, and you can see. And now you could also do something similar by a function called update. So I had a model called lm_fit, and what I wanted to do was to take off age from it. And so the lm_fit1 was the one that explicitly removed it. But look at what lm_fit1, the new way, in line 42 is doing. It is doing exactly what I had done before, but this time it's using the old one, and from the old one, it removed age by having the minus age symbol. Okay, that was multiple, you saw, and so I think this was enough of a walkthrough. Let me show you how to do interaction terms. Interaction terms, if you remember the advertisement example, is when you have two variables that when they are taken together would contribute even more. So if you had a new variable that you would introduce in your predictors. And the way you do this in R is by having this symbol star, like multiplication. So lstat and age, age we saw on itself when it is others are included was not helping very much. But if we compare it, the age of the house with the low stats incomes, is that combination something that would make a difference, is what this one is trying to show. So the first thing is syntax. So the way you would handle interaction variables is by having this symbol called star that would take the variables that are interacting. The rest of it is similar. And so we are still fitting a linear model, but I'm doing two things in one line now, in line 46. What I'm doing there is do the interaction, but I also wanted to get a summary on this new one. And so that's what the function call is doing, the summary. And so let's see what it gives me. Here it is what it produced. And you can see now that the interaction between lstat and age, by the way, it's shown by this symbol called lstat : age. So lstat and age are now the main effects, and lstat : age is the interaction effect. The p-value for it is not all that bad. And this is curious. You may this is a good illustration. So on its own, age was not contributing, and therefore we were able to remove it without losing anything. But when it is seen in the interaction of it is well listed is significant, and at least it got 1 star. This is the place where I want to remind you this hierarchy stuff. So if you were to include this in your model now, and you decided age was not a good contributor and you leave it out, then it becomes difficult to interpret. And therefore, you would want to have age included in your model, which is what this code has shown you. So there are at least 3 or 4 points that I have made with this one. It was just a single line, but I hope you have followed me along and got them all. Non-linear transformation. So interaction was one way in which the linear models could be extended. The other way is when you have non-linearity in it, the linear model can handle it. And we saw at least in theory last time, and let's see how it is done in this case in R, what syntax you would use to show that. That's what I am going to be talking about now. Now we will call our fit LM fit 2. By 2 here is my way of saying now we are doing with polynomial of degree 2. We saw that this median value was non-linearly related with L stat. And so we want to see, if a fit that takes a square of this, the L stat value would improve our model. This is what our new model is doing. So L stat is taken, but in addition to that, we are also going to take L stat squared. And the L stat squared, this is the syntax for doing it. You do the power sign and then you do a Reiner 2. But this power sign in R also has another meaning. And so to force R, for it to know that you're working with a nonlinear term now, you would put it within this I, identity matrix. That's what it stands for. So I, and then you put in parentheses the power you want to raise it with. And now you've got a model that would take L stat and L stat squared. And let's see what that would do for us. So I'm line 15, I did fit a model. And now I'm going to get a summary of this. So I'm now going to expect, before I display it, you should kind of guess what is going to come. This new fit now will have a variable called L stat, but it should also have a predictor called L stat squared, is what we would expect, and it does. And so we have the intercept, and we have the L state that was before, and the I stat squared is now the new term, and you can see it's actually pretty significant. It's got 3 stars on it. The p-value is so small, so the nonlinearity is fairly strong, and by having to do this, we would do a good job capturing it. Let me see if we would do anything that would quantify this. This is the function called ANOVA that will now compare the linear fit without having the nonlinear terms added, the first one, and the one that has got the polynomial of degree 2. And so when you do that, you get these models, how they compare with one another, and you get different ways in which you can see the improvement that you have got in terms of using nonlinearity. Okay, I'm going to now show you what this plot would look like when this fit is added, and you can now see the kind of diagnostic plots we had before with the 4 pieces to it, and the residual now, that is the residuals versus the fitted values that was kind of curved upwards when it was just a linear one without having the second term added, is now disappeared. And now we see a nice, smooth, horizontal looking line, which is what we wanted to see. And so that's a good news now. So our polynomial or degree 2 fit was a good thing to do. You could go on now if you feel like there is, oh, I see a little bit of a curve there, maybe I'll have to do degree 5, for example. You could do that, and we saw an example in our lecture last, at least on a slide. And so LM fit 5 in line 57 tries to do that. What if I try to go all the way to degree of polynomial 5? It does that, okay, that's one thing, but it also shows us a shorthand. What I showed you before with the I, and then in parentheses, putting the variable that you want to square by squaring it is more or less like manually doing it. But if you wanted to have a shorthand that will do that, you could call this function called poly, and then you can give it the main variable, and then how many degrees that you would go up to. And so in this case, we wanted to do up to degree 5. So that will be L stat squared, L stat cubed, 4th, and 5th. That's all of it that's happening in line 57. We could do that, and we get a summary on it. Now you can see what those values would give you, and you get some of the p-values, whether that was significant or not. Okay, I want to continue and show you the last piece I want to show you today. And here is another place for you to take a sip of coffee if you have around. We did do now interaction, we did do nonlinearity, we saw how to have diagnostic plots and so on. But one thing we saw last time was qualitative predictors. Those are categorical values, and we said we will introduce dummy variables and so on. So we're going to see that on a different data set than the Boston one. And this data set is called car seats. And this is what I'm going to be working on with now. And so fixed car seats, this is I knew that's going to show me an error message, because this would have opened up an editor for you to see what this car seats data set is. It's available in the ISLR package, and I'm not opening it up because it is complaining something that's not something you need to worry about. But let's see what it has. This car seats data set has got these variables, and one of them has to do with, this was actually a study done about safety. One of the doors has got, a safety lock on it, or on something. If children, you don't want them to get out of the car, and so you've got that feature is what shelf lock is. The point of this is just to tell you one of these variables is qualitative. In other words, it's categorical, and that particular variable is called shelf lock, and you want to include that in your model, in your linear model. What do you do? So we're going to fit a model for sales, how many cars of these car sets were sold. And so there is different things that we want to include from these variables. Income is one of them, advertising price and things like that. We fit it. And so that's what you see in line 65. We get a summary of that. And so we get these values, the intercepts and the p-values associated with them. And so if you see what has happened now to the thing that's called shelf lock, which was a categorical variable, R has introduced these dummy variables I told you last time. You don't have to do them manually yourself. So they were included, just like these other variables were. Most of them were quantitative ones. They were just taken like everybody else. But the qualitative one, R discovered it and created dummy variables for it. And that's why you see now this new variables called shelf lock good and shelf lock medium added to it. And so its contribution, whether it is significant or not, is what you see in the summary. And so you could see, actually, if you wanted to query how the dummy variables were set up, you could do something called contrasts. And contrast, this is my last line. Contrasts is a function call that will tell you for a given categorical value what dummy variables were introduced to it. And so in this case, this shelf lock has got 3 values that it could assume: bad, good, and medium. And by having a dummy variable that is only 2, you can achieve what you wanted to achieve. And so a good is now when the dummy variable good is set to 1 and the medium is 0. A medium is when the dummy variable is set to medium equal to 1, otherwise 0. And when both of them are 0, that means it's bad. And that's what you see here. And that summary that I showed earlier shows you what their contribution was to the model. I am so impressed that I finished this. I was thinking that I may run out of time, but I didn't. Maybe I was speaking fast, but I hope you have followed me along. You've got the piece of code. It's not commented, but you have this recording that will be available anyway if you need to read. But read section 3.6, and I think you will be just fine. All right. Anybody's got any questions for me? Let me see if there was any question in the chat that came while I was talking. Okay, so solutions was one question we asked. I think Helen does a good job when you point to indicate. I am going to think about it if we really need to post solutions. But yes, for some of them where you would benefit by learning how you made mistake, we will. Okay, so my short answer is yes, we will think about that. We may not necessarily do for everything, but we'll provide solutions for the ones that are worth knowing how to do them correctly. Is everybody happy with the grades that you got on first 4 assignments? Is there anybody who thinks Helen is unfair in grading? No. No, you shouldn't say yes to this question. You should know 3 questions. If I ask you something like this and you say yes, you're in trouble. But you should also be honest. Okay. 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 Thanks. So I'll think about the solutions part. I think I completely agree. Sometimes it's good to know how things are correctly done. So we'll post as needed. The first, for example, I think the things that are about how to, do joins correctly and things like that. For some of you have gotten them wrong. I think knowing them how the correct way to do it is helpful. Okay, I'm going to stop here. Be looking forward to classification and make sure that you promise me to do a walk on the place where you say your favorite. It doesn't matter how long it is, but do that this weekend. And you'll hear back from me on the project proposal status. You can almost assume that you'll be approved. I am more interested in giving you feedback. If there is somebody who is really needs rethinking, I will let you know. But I don't think it's unfair for you to assume that you'll be approved. And I really, really want you to get started next week. Before we start, I will set up times for me to meet during office hour or some other time. All right, I have to stop here now. I will see you on Monday and have a great weekend.